Hello, I am Bhargava. I am here to tell about multitrack Turing machines. Before knowing that, let us know what is a Turing machine. Turing machine is actually invented by Alan Turing, and these are actually used to accept recursive enumerable languages which are generated by type 0 grammar. Turing machine consists of a tape of infinite length on which read and write operations can be performed. A tape consists of infinite cells on each, which either contains input symbol or a special symbol called as a blank. It also consists of a head pointer which points the cell currently being read, and it can move in both directions, that is left or right. A single tape, single track Turing machine consists of seven tuple values, that is Q, sigma, tau, delta, Q naught, F, and the blank symbol. In Turing machines, we have different types. Few of them are already mentioned. Single tape, single track Turing machines, in which there is a single tape with a single track and a single pointer pointing to the track, which can move either in the left direction or the right direction. The second type would be single tape multi-track Turing machine, in which there is one single tape with multiple tracks and a common pointer which can read n elements in the n tracks at once. Next, we have multiple tape Turing machine, in which there is there are multiple tapes, but with a single head pointer which can move either in left or right direction. So today's our topic would be single tape multi-track Turing machines. Let's discuss them in detail. So multi-track Turing machine is a specific type of multi-tape Turing machine which contains of multiple tracks but with just one tape head which reads and writes on all the tracks. Here a single tape head which reads n symbols from n tracks at one step. It accepts recursively enumerable languages just like a normal single track single tape Turing machine accepts that. As we discussed, it has seven tuple values. Those are Q, sigma, tau, del, Q naught, F, and blank. Q refers to the set of finite states. Sigma refers to set of input symbols. Tau represents set of tape symbols. Q naught represents the initial state. F represents the final state. This symbol represents a blank symbol, which is a special symbol in the Turing machine. And finally, the transitions, which are defined as Q cross sigma, which tends to Q cross tape symbols cross left or right direction. Let's discuss them in detail with an example. Let's say we have to design a Turing machine to compute multiplication of two integers or any two numbers. Multiplication of two numbers is represented by n cross m, where n is called as a multiplier and m is called as a multiplicand. Basically, multiplication of n cross m can be understood as addition of n m times or addition of m n times. To make it easier, we'll refer to an example, that is 6 cross 4. We know its value, that is 24. But now our objective is to design a Turing machine which generates a result and also reads all the steps of multiplication. Let's first discuss the algorithm to design this Turing machine. For this particular problem, I will be choosing 3-track Turing machine. The steps goes as follows. The step 1 would be placing the multiplier in the track 1. Step 2 would be placing the multiplicand in the track 2. Step 3, if t2 equal to 0, we make t3 equal to 0 and the result is in t3. Similarly, in the step 4, if t1 equal to 0, then t3 equal to 0 and the result is in t3. Step 5, we perform an operation in the track 3, that is t3 equal to t3 plus t1. In the sixth step, we decrement the t2 value by 1. And finally, the last step would be if t2 equal to 0, we finally stop. Based on this algorithm, let's design a Turing machine. As we have discussed, we have chosen a 3-track Turing machine. So according to the algorithm, the step 1 would be placing the given multiplier in the track 1. According to our example, we have taken the multiplier as 6 and multiplicand as 4. So place 6 in T1. The second step would be placing multiplicand in T2. That is, place 4 in T2. An initial value in T3 for the initial result would be 0. Now our head pointer points in this direction. Let's read all the values from all the tracks and then let's move forward to the right direction. The T1 value doesn't change. The next step, according to the algorithm, would be updating the T3 value by T3 plus 1. So T3 that is initially by 0, that is equal to 0 plus T1 value that is 6. The next T3 value would be 6. And the next step would be decrementing T2 value that is 4 with 1 that is 3. We must follow this process until we get a 0 in T2. So now we read all the values from the next track and move forward in the right direction. Now we have 6, 3 and 6. The next step would be adding T1 and T3 that is 6 plus 6. That makes 12 and decrement the T2 value by 1 that makes 2. The next step would be read these values and move forward in right direction. Now T3 equal to T3 plus T1 that is 6 plus 12, we have 18, and the T2 value is decremented by 1, that is 2 minus 1, which gives us 1. We read these values and certainly move forward in the right direction. T3 value would be 18 plus 6, that is 24, and T2 value would be 1 minus 1, that is 0. Now, as a final 0 has occurred in T2, we must stop the process and fill the remains with blank. According to the algorithm, if T2 contains a 0, then the result in the T3 is the final result. So 6 into 4 is basically 24. We have certainly followed the steps in the algorithm and also designed a Turing machine for it. Certainly, we have got the result for the multiplication problem. Let's design a state diagram for this particular Turing machine. The first step would be starting from the initial state. We read the value 6, 4, 0. We did not update them in the initial state and move to the right direction. We reach the next state, Q1, where we experience another 6, 4, 0. We update them into 6, 3, 6 and move in the right direction. The next step would be Q2. In the next state, we update 6, 3, 6 to 6, 2, 12 and move forward in the right direction. Next, in the next state, we update the information 6, 2, 12 to 6, 1, 8 and move in the right direction. In the next state, we update 6, 1 and 18 to 6, 0 and 24 and move in the right direction. As we have experienced a 0 over here, we will be reaching to the final state. So this is basically the state diagram for the following Turing machine. The next problem given to us is to find the factorial of any given integer. For example, let's take 4 factorial. That will be 4 into 3 into 2 into 1. That is 4 into 3, 12 into 2, that is 24 into 1. And the final result is 24. Certainly, we must design a Turing machine to accept all the process and also generate the result. The algorithm goes as follows. I have again chosen a 3-track Turing machine for the given problem, and the steps goes as follows. In the step 1, I will place the given number in T1. The second step would be placing the result in T3. With initial result equal to 1. The step 3, we will place the same n in T2 by updating this value. Step 4, if T2 equal to 0, then the result would be in T3. Step 5, we will be updating the result in T3, that is T3 equal to T3 times T2. In the sixth step, we will be decrementing the value in T2, that is T2 equal to T2 minus 1. And finally, in the seventh step, if T2 experiences 0, then we terminate the process. And the final result would be placed in T3. Let's design the Turing machine for the certain algorithm. As we discussed, let's say our n factorial, that is 4 factorial, gives us the result 24. And we have chosen a 3-track Turing machine where in the tree 1, we place our n. The second step would be placing the result in T3 with an initial result 1, and T2 consists the same number n, and the pointer head points in this track. Let's read all the values and move forward to the right direction. According to the algorithm, we must multiply T3 with T2 and update the value in T3. So T3 equal to T3 into T2, that is 1 times 4, that is 4. The T1 value remains same and the T2 value is decremented by 1. So that becomes 4 minus 1, that is 3. We read all these values and move forward in the right direction. Now, we must update the value in track 3, that is by multiplying T3 into T2, that is 4 into 3, that is 12. And next, decrement the value in T2, that is 3 minus 1, which gives us 2. We certainly read these values and move forward in the right direction. We have 4 in T1. In T2, we have 2. In T3, we have 12. Now our next step would be updating T3 value. That is 12 times 2 gives us 24. And at the T2, we update 2 to 1. We read these values and move forward in right direction. We update the value in T3, that is 24 times 1 gives 24. And the T2 value is decremented, that is 1 minus 1, 0. According to the algorithm, we have experienced a 0 in T2, so we must terminate this process here itself. The result in T3 is the final result if the T2 value goes to 0. So, according to the Turing machine, the value of 4 factorial is 24, and it is certainly right. We have successfully designed a Turing machine for this problem. So let's design a state diagram. We initially begin with the initial state Q naught. We have to read the values 4, 4, 1. We do not update them and move in the right direction in the first step. So it remains as 4, 4 and 1 and move to right where we reach our next state, that is Q1. Now we have 4, 4, 1 in our tape where we update them into 4, 3, 4 and move in the right direction. We now reach the next state, Q2, where we have 4, 3, 4. We update them into 4, 2, 12 and move in the right direction, where we reach the next state, that is Q3. In Q3, we have 4, 2 and 12, where we update it into 4, 1 and 24. We certainly move forward in the right direction and reach Q4. In Q4, we have 4, 1 and 24. We update it into 4, 0 and 24 and move in the right direction. As we have experienced this over here, we shall move to the final state and accept the final result. So this is the final diagram, the final state diagram for the following problem. Thank you.